Imagine if the first message from an extraterrestrial civilization wasn't a greeting, but a set of coordinates, not pointing to a star or a planet, but to a patch of perfect, impenetrable blackness. A warning, perhaps, about a place where the familiar rules of our reality cease to apply. These cosmic enigmas, known as black holes, are among the most mystifying phenomena in the universe. It's vital to grasp from the outset that they are not objects in the conventional sense. Instead, they are locations where space-time itself has been warped to an unimaginable degree. This profound distortion of the universe's fabric leads to incredibly strange events in their vicinity, occurrences that can challenge our fundamental understanding of how everything works. The effects are so outlandish that they might seem like fiction, yet they are supported by rigorous mathematical principles and increasingly confirmed by direct observations that prove the math was right all along. In this journey, we will venture into these mysterious domains, exploring the bizarre science that governs how they are born, what happens around them, and the theoretical pathways that might offer an escape from what are often called the ultimate cosmic prisons. Black holes appear across a breathtaking range of scales. The most diminutive black hole ever detected has a mass around 3.8 times that of our own Sun. On the opposite end of the spectrum, we find black holes that have been around nearly since the beginning of time, with masses that are billions of times greater than the Sun's. These titanic entities are not just incredibly heavy, they are also unimaginably large, with event horizons vast enough to swallow our entire solar system. The black holes that come into being in our current cosmic era represent the final chapter in the story of very massive stars. When one of these giant stars is born, it exists in a state of delicate balance, governed by two competing forces. The first force is gravity, which constantly tries to crush the star's immense mass inward toward its center. Deep inside the star's core, the pressure is so intense that it forces hydrogen atoms to fuse together, creating a heavier element, helium. This new atomic structure is more stable and requires less energy than the two separate hydrogen atoms it was made from. As a result, the excess energy is released. This liberated energy becomes the second force, radiating outward from the star's core as light and heat, perfectly pushing back against gravity's inward pull. In this state, the star can remain stable for millions or billions of years until the nuclear furnace in its core starts to cool as its hydrogen fuel runs low. If the star has enough mass, once its hydrogen supply begins to dwindle, it will start fusing the helium it created into even heavier materials, like carbon, neon, and eventually oxygen and silicon. A crucial moment arrives, however, when the star begins to create iron. The problem with iron is that its formation doesn't release any extra energy. In fact, it consumes energy. This means there is no new energy radiating outward to provide a counterforce to gravity. Iron just builds up in the star's core, growing larger and larger, with no outward pressure to stop gravity's relentless crush. The balance is quickly lost. The energy unleashed by this gravitational collapse is staggering, with its power being directly tied to the star's original mass. Like a colossal hammer smashing into an anvil, the star's own mass falls inward with such incredible force that the rebound creates what we call a supernova. In one of the most powerful explosions imaginable, matter and energy are blasted across the cosmos, forging elements even heavier than iron, all the way up to uranium. The final destiny of what's left of the star depends on its initial mass, and therefore, the power of this explosive collapse. If the mass and the resulting force of the impact were too low, the remnant becomes a neutron star, a compact ball of matter, perhaps only 25 kilometers across, yet so astonishingly dense that it has the mass of 1,000,000 Earths. But if the mass and the force of the collapse were great enough, the known laws of physics as we understand them break down, and what is left behind is a black hole. When you look at a picture that claims to show a black hole, the dark circle you see isn't actually the black hole. Scientists believe that a black hole's true form is probably even smaller and denser than a neutron star. In fact, it's thought to be infinitely small and infinitely dense, a singularity, a single point from which forces warp space-time itself. We can't know for certain, however, because of a boundary called the event horizon. Every object with mass has a gravitational pull. This has been a known principle since the days of Isaac Newton. But when Albert Einstein unveiled his theory of general relativity in 1915, a contemporary physicist named Carl Schwarzschild used it to deduce the theoretical existence of objects so incredibly massive that their gravity would be strong enough to trap even light. If even weightless photons of light cannot escape, then nothing can. So, when you look at a rendering of a black hole, you are not seeing the singularity itself. You are seeing its event horizon, the exact boundary line where gravity's pull becomes so powerful that light can no longer get away. Beyond that line, there is only absolute darkness. The event horizon's effect on space is one thing, but black holes also have a profound impact on another fundamental dimension of our universe: time. According to Einstein, space and time are woven together into a single fabric, and mass causes this space-time fabric to warp. Since the singularity is a point of infinite mass, it distorts space-time so much that the event horizon also becomes the point where time itself essentially stops. Inside the event horizon, space and time unravel completely, creating a region with no where or when. This leads to a truly strange effect. For an observer watching from a safe distance, as matter falls toward a black hole, that matter will appear to slow down as it gets closer, eventually seeming to stop completely just before it reaches the event horizon. You would never actually see it cross over. There would be no satisfying moment of absorption. Instead, the object would just grow dimmer and dimmer until it faded from view entirely. When they were first theorized, astronomers and physicists were not sure if black holes really existed. It took another 40 years, until 1964, for the first real evidence of a black hole to be discovered. Using new X-ray satellites, scientists found an object in the constellation Cygnus that seemed to be giving off an enormous amount of X-rays. What was strange was that despite these powerful X-ray emissions, scientists couldn't see the object itself. This was a puzzle, because if it were a star, it should have been emitting visible light along with the X-rays. Scientists gave this mysterious object the name Cygnus X1. By 1970, with better telescope technology, astronomers saw that whatever Cygnus X1 was, it was locked in a binary orbit with a visible companion star. This was a critical discovery because it allowed scientists to calculate its mass. They worked out that this invisible object was 15 times more massive than our Sun. Since the most massive a neutron star could be was about 3 times the Sun's mass, scientists concluded that Cygnus X1 was very likely the first black hole ever found. Since that time, many more black holes have been located. Huge ones are thought to be at the centers of most galaxies, and we have even managed to take pictures of a few of them. Dark shadows set against the bright, swirling ring of matter that surrounds and spirals into them, which is called an accretion disk. This is exactly how black holes, even though they are invisible, can still be spotted using X-rays. While the black holes themselves don't emit any electromagnetic radiation, The X-rays we detect are actually coming from these accretion disks, where matter falling in is heated to millions of degrees Celsius by intense friction. In contrast, black holes that aren't actively feeding on nearby matter are effectively invisible, as they have no luminous accretion disk to give away their position. The study of black holes continues to be a vibrant and changing area of physics, with a great deal left to figure out. Based on what we know so far, you might wonder if a black hole could ever stop being a black hole, or if it just keeps growing forever until it consumes all the matter and radiation in the universe. Logically, that would seem to be the case. But in 1974, in a landmark paper titled Black Hole Explosions, the physicist Stephen Hawking suggested that there might be a way for energy, and therefore mass, to actually escape from a black hole. To understand his idea, we have to journey into some extremely strange territory, which means looking at some of the core principles of quantum mechanics. Let's begin with a difficult question. What exactly is nothing? Picture, for a moment, an area of space that is completely empty. There are no atoms of cosmic dust, not even any radiation passing through. As far as anyone could tell, there is nothing there. And yet, is it truly, absolutely empty? There must be something fundamental there, a fact we can tell when a beam of light travels through it. If you're familiar with the nature of light, you know that it is made of waves of electrical and magnetic charge, which constantly spread and interact with each other in a straight line. But think about the word wave. A wave in the ocean is a transfer of energy moving through the water. If you were to watch a single water molecule, it doesn't really travel forward, it just moves in a small circle. But because it passes energy to the atoms next to it, energy ultimately moves toward the shore in a continuous flow. In the same way, a sound wave travels by passing energy between air particles, with each particle just vibrating slightly before passing that energy to the next one. But in our vacuum of space, where there seems to be nothing, and where our photon of light is traveling in waves, have you ever stopped to think about what exactly is doing the waving? This suggests there is a fundamental something that exists even in total emptiness, a fabric that makes up all of reality. Quantum physicists call this something a quantum field. Quantum fields are difficult to visualize, but they are absolutely essential for understanding the final fate of a black hole. So how do quantum fields connect to the idea of exploding black holes? Going back to Hawking's paper, he theorized that black holes would slowly leak energy over time, starting with tiny amounts. Because energy and mass are just two forms of the same thing, according to Einstein's famous equation, E = mc2, this would have to mean the black hole is losing mass. But as the black hole got smaller, the rate of energy release would speed up, getting faster and faster, until in the very last moments of the black hole's life, it would unleash a final gigantic burst of energy before vanishing completely. But how could this be possible? It's a well-established fact that nothing can escape the event horizon. So how could any radiation ever get out and eventually cause the black hole to explode? The answer is strange and depends on counterintuitive ideas from quantum theory that go against all of our everyday experiences. But if it's true, it points to a universe that is far stranger than we ever thought. To start understanding Hawking's theory, we need to grasp the idea of quantum fields. Remember that light moves like a wave even through a perfectly empty patch of space, which tells us there must be something present even in what appears to be nothing. Otherwise, the light would have nothing to wave through. Scientists call this fundamental fabric of reality a quantum field. In fact, They believe there are multiple quantum fields, all overlapping and filling every single part of the universe, past, present, and future. Each quantum field defines a certain type of something. One field might define every electron in existence, while another might define the quarks that make up an atom. Where we find nothing, the quantum field is mostly quiet, like an unplucked guitar string or a graph showing a value of 0. But wherever there is mass or energy in space-time, the quantum field at that location is vibrating. When this vibration reaches a certain level, the universe manifests it as, for example, an electron or a photon. It's important to understand that in this theory, the vibration isn't just reacting to a piece of matter. It is the matter. An electron is simply a vibrating part of the quantum field that defines electrons. The same is true for all energy and all matter. According to Einstein, energy and matter are two sides of the same coin. Therefore, the entire universe we see is, in this view, nothing more than vibrating quantum fields. In this sense, the theory paints a picture of the universe as a song being played on these fields, which is a beautiful image, if nothing else. But why is this important? Why does it matter to define the universe this way? Well, because of a principle in quantum physics called Heisenberg's uncertainty principle. Sometimes the strings of the universe start to pluck themselves. Without getting too deep into this area of quantum physics, it basically says that when you look at extremely tiny objects on an atomic scale, you can't know too much about them at the same time. For instance, you can't know the exact location and the exact direction of travel of an electron. The moment you try to measure an electron's position, it interacts with your measuring device, which changes its path, making its direction of travel uncertain. And if you know its direction, you can't know its precise location. This isn't just because our measuring tools aren't good enough. It's a fundamental law about the nature of the universe. According to Heisenberg's uncertainty principle, you can never have complete information about particles at the subatomic level. When this principle is applied to quantum fields, however, things get very strange. Quantum fields are always fluctuating, and as dictated by Heisenberg's uncertainty principle, pairs of particles and antiparticles can spontaneously pop into and out of existence. The exact details are complex, but essentially, the universe allows this to happen as long as they exist for only a fleeting moment, governed by the laws of uncertainty. You might think this is impossible. Matter doesn't just appear from nowhere, and we would have surely noticed it. However, in an experiment by Hendrik Casimir, evidence suggested this phenomenon might actually be real. Casimir placed two conductive metal plates extremely close together, so that only certain sizes of smaller virtual particles could spontaneously appear between them. This limited the number of these particles that could emerge, but because all types of particles could pop into existence outside the plates, this created a pressure difference on the two sides of each plate. In theory, the greater pressure from the larger number of virtual particles outside the plates should push the two plates together, and in the experiment, this is exactly what was observed. One might think that particles appearing out of nowhere seems to violate the law of conservation of matter, and you would be right. To keep things balanced, whenever a virtual particle appears, a second particle also spontaneously appears to pair with it. However, while one of these particles is matter, the other is antimatter, a 1 and a 1 on our cosmic balance sheet, which keeps the total at 0. The universe is happy, and what's more, these quantum field fluctuations quickly collide and annihilate each other, removing both from existence again, so we usually don't have to worry about them. As a side note, there's a theory that antimatter is just matter traveling backward in time, but that level of strangeness is a story for another day. The important point is that quantum fields are constantly vibrating and constantly canceling each other out, which is why most of the time empty space stays empty. But what would happen if only some of these fields were prevented from vibrating? This is where black holes come in. Black holes act something like putting your thumb on one of the universe's guitar strings. Because of their event horizons, certain vibrations in the quantum fields are suppressed, while others are not. Hawking imagined drawing a line through time in a patch of space where a black hole was formed. He pictured a quantum field that vibrated along this line, stretching from before the black hole existed into its future. Before the black hole's birth, everything is normal. Quantum fields can vibrate freely and cancel each other out. But the appearance of the black hole's event horizon changes the curvature of space, and outside of it, Hawking realized that certain vibrations were now missing their opposite numbers. As he worked through the math, he concluded that not everything was being canceled out anymore after the black hole had formed. In fact, outside the event horizon, traveling away from the black hole, he identified vibrations that perfectly matched the profile of thermal radiation escaping into space. Radiation is energy, and energy can't come from nothing. Since the black hole was seemingly creating this radiation, the black hole itself would have to pay the bill. Every bit of Hawking radiation would therefore correspond to an equal amount of energy being lost from the black hole, which, over a very long time, would cause it to evaporate into nothing. If it's real, Hawking radiation is like money spontaneously appearing outside a bank, while at the same time, inside the bank, an equal amount of money disappears from the vault. It is also incredibly difficult to prove experimentally. As Hawking predicted, this radiation would be colder than the cosmic background radiation that fills the universe and would have a wavelength as long as the black hole's event horizon itself. Given that some black holes have event horizons the size of solar systems, we currently don't have any way to detect this kind of radiation. We would only really be able to see it once the universe had grown cold and empty of other interference, which would likely mean we would no longer be around to detect it. Nevertheless, despite the challenges, the mathematical basis for Hawking radiation seems solid, and scientists have recently made progress toward proving it exists in a lab. At the Technion Israel Institute of Technology, researchers studying Hawking radiation came up with a way to get around the difficulty of measuring a real black hole. They did this by building an analog, a sonic black hole, made to mimic the properties of a gravitational one. Their method took advantage of the fact that sound travels much slower than light, making it far easier to create a medium that moves faster than sound. When such a medium is moving, any sound waves traveling in the same direction can never quite escape it. Intriguingly, Hawking's mathematics applied to these sonic black holes just as well as they did to gravity-based ones, which meant that Hawking radiation should be detectable from them. After running the experiment 97,000 times over 124 days of continuous testing, the researchers detected multiple instances of Hawking radiation and saw that it matched Hawking's predictions about its behavior. While this doesn't prove for certain that Hawking radiation is real for actual black holes, the fact that Hawking's math held up for this sonic analog strongly suggests his theory might be correct. Hawking radiation might just be real. So, if you were to fall into a black hole, is escape ever possible? Probably not. However, if you were to wait until nearly the very end of the universe, the black hole might, through the steady emission of Hawking radiation, eventually release all the mass and energy that once made up your existence from inside the event horizon. Does that count as escaping? that's likely not a very comforting prospect. It's probably best to just avoid falling in to begin with. Furthermore, this is not the only strange thing about black holes. Their very nature hints at something quite unsettling about our own reality. When you walk on a sandy beach and leave a footprint, there's no doubt in your mind that your foot made the print. The order of cause and effect is so obvious that stating it seems absurd. You made the footprint didn't make you. But what if it did? What if, on a cosmic scale, the basic relationship between the foot and the footprint is a bit more ambiguous than we instinctively believe? Shockingly, due to the nature of black holes and Hawking radiation, there's some evidence that this might actually be the case. To start, we need to look at a principle called relativity, but not Einstein's famous theory. Instead, we'll look at Galilean relativity, first outlined by Galileo Galilei in 1632. The main idea of this form of relativity is that there's no observable difference between being perfectly still and moving at a constant speed. Picture two rooms, one on a ship and one on land. Both are soundproof and have no windows. Imagine the sea is perfectly flat, with no rocking at all. The only difference is that one room is moving and the other isn't. Can you tell which is which from the inside? You might think you could feel the motion, but that's not the case. For example, right now, you are speeding through space at about 110,000 kilometers per hour because of the Earth's orbit around the Sun, yet if you're sitting at home, you'd probably say you aren't moving at all. In fact, Galileo realized that no experiment you could do inside the rooms could distinguish between the two situations. He even found that if you dropped a ball on the ship from your point of view, it would seem to fall straight down, even though from the perspective of someone on land, it would look like it was falling diagonally. Galileo understood that if you remove all frames of reference, say by being in deep space, there's no way to know for sure if a planet is moving toward you or if you are moving toward a planet. According to relativity, both views are equally correct. You might have felt this yourself if you've ever looked out a train window just as another train started to pass you quickly. Even though both trains are moving forward, the other train is going faster than yours, and because you've lost a fixed point of reference, it can momentarily feel like you're suddenly moving backward. Einstein took this idea even further with his equivalence principle. Here, he went back to the idea of two rooms, but this time he focused on gravity. If you were in a windowless room floating in the vacuum of space, and someone started accelerating your room upward, for example by attaching a rocket to the bottom, if the rocket accelerated at just the right rate, it would feel exactly the same as standing in a room on Earth's surface. In other words, there is no noticeable difference between the acceleration from gravity and the acceleration from a rocket, assuming you could ignore the rocket's vibrations. Both of these principles depend on the concept of inertia, that objects resist changes to their state of motion. They tend to stay still if left alone, and tend to keep moving once they've started. Any attempt to change an object's current motion requires a new force. Otherwise, it will stay inert. But why would it feel to the person in the room with the rocket as if they were experiencing gravity? Or maybe a better question is, why does it feel to us on Earth as if we are being accelerated upward by a rocket? Surely the Earth isn't expanding in all directions at once, pushing us with it. While that's true, Einstein realized the two situations felt similar because they were fundamentally the same thing, a type of acceleration. However, there's another kind of acceleration that gives a better explanation for how gravity works than just applying a pushing force to an object, like a rocket does. Think about a spinning ride at a fairground. If you've ever been on one, you'll know the power of changing direction as a form of acceleration. When you stand against the wall of the ride, Once it gets up to a certain speed, you feel a constant force pushing you against the wall, even when the ride is spinning at a steady rate. This happens because your mass is trying to travel in a straight line at every moment. But the curve of the ride forces you to change your direction. The conflict between your inertia, which wants to keep you moving in your current state, and the wall, which is trying to change your direction of travel, is felt as the force you perceive. As far as acceleration goes, there's little difference between the Earth accelerating you upward and you trying to accelerate downward. Einstein realized that this kind of acceleration from a curving path, was the best way to explain gravity. He developed a theory suggesting that matter and energy cause a warping in the space-time around them, much like how a heavy ball might dent the surface of a stretched rubber sheet. The more mass, the bigger the curve. Once space is curved, any object trying to travel through it would be deflected by that curve. In the words of physicist John Wheeler, space tells matter how to move, matter tells space how to curve. For small masses, this curve in space would be very slight, but for dense masses, this curvature could become so deep that it would be impossible for an object that got too close to ever escape. These are exactly the conditions near a black hole, with its event horizon. Returning to our earlier analogy of the footprint and the foot, if a black hole is the foot, the curvature of space around it is the footprint. It's amazing to see all of this in action and to understand how Einstein came to conclusions that would be almost universally proven by scientists even a century later. But there's nothing particularly weird about any of this so far. Understanding the exact mechanics behind it doesn't make it any stranger. The black hole tells space how to curve, and once it's curved, any object moving near it is told how to move. Nothing here is outside what we'd expect from everyday observations. But when we start to look at Hawking radiation, something truly strange happens. The most important thing to remember about it for our current discussion is that it is non-local. This means it doesn't come directly from the black hole itself, but appears from the area of space around it. To be clear, I don't mean from beyond the black hole's singularity, which is hard to define anyway, since space as we know it doesn't exist there. Remember, the black ball you see in pictures is just the dividing line between inescapable curvature and escapable curvature, the event horizon. I don't even mean right up against the event horizon, although that's sometimes how this theory is shown. People sometimes talk about two particles appearing right at the event horizon, with the antimatter particle just inside so it falls in, while the normal particle is just outside and escapes. This is not what's happening. Instead, the area of space where this radiation can spontaneously appear covers several times the size of the event horizon, a distance up to billions of kilometers away. And since the largest black holes can easily fit multiple solar systems side by side within their event horizon, the idea that a photon of radiation can appear out of nowhere at such a distance outside the event horizon is truly mind-bending. It happens even in a place where there is literally nothing. So, in effect, Hawking radiation isn't so much coming directly from the black hole. Instead, it's coming into being from the curvature of space that the black hole is creating, and this can happen very far away from the black hole itself. But if that's true, then things work in a way that is completely opposite to what we might expect. As you'll soon see, consider what happens in this order. As energy leaves the curvature of space, the curvature gets smaller because of the principle of conservation of energy. And as this reduction in curvature happens, the black hole then gets smaller. This is insane. This is like the footprint getting smaller, and as a result, the foot shrinks to match. It feels fundamentally wrong. things can't possibly work that way. And yet, Einstein hinted that such a possibility might exist in one of his equations. He said that the curvature of space-time was proportional to the mass energy of an object. However, proportional is not causational. There's no rule that one has to cause the other in this relationship. We're comfortable with the idea of changing mass causing a change in curvature, but it works just as well if you go the other way and change the curvature to change the mass. If this is true, then it suggests a universe where mass is just a projection caused by the curvature of space-time. When you shine a light at an object, like your hand, and it casts a shadow on the wall, the shadow is a projection caused by your hand interacting with the light. Normally, in this analogy, you'd be forgiven for thinking that we are the hand, that our mass creates the curvature of space around us. And yet, do we really know that it doesn't work the other way around? Are we just projections, shadows on the wall of the universe, brought into being by something more fundamental happening in the curvature of space-time? And yet, we go through our lives thinking we are the real thing. We genuinely don't know. Since all you perceive is the reality you experience, it would be hard for you to tell the difference between the two scenarios. But if relativity has taught us anything, it's that if there's no way to distinguish between two situations, then we can't completely rule out the possibility that we are in one and not the other. Either that, or the two might be more closely linked than we previously thought. Of course, this is all just a theory. There is no definite proof that Hawking radiation is even a real phenomenon, although some experiments have given hints that it might be. Nevertheless, it's something fascinating to think about, and even if it turns out that reality is a projection, it won't significantly change your daily life. You will still think and feel, and that is more than enough reason for you to keep doing what you're currently doing. But it serves as an example of how, when we start to examine the very fundamental building blocks of reality by looking at the strange warping effects of black holes, it can force us to question our preconceived ideas about our very nature. After all, when you ask the question, "Am I real?" and the answer is, "It's not certain," that is more than a little unsettling. Regardless, black holes definitely influence our reality and our universe, and not just because they relentlessly pull everything within their reach into their grasp, giving nothing back. They represent the ultimate end, the final destructive force in the cosmos. And yet, what if I told you that they might actually turn out to be our salvation? Black holes could hold the key to achieving faster-than-light travel and solving the energy crisis in ways we couldn't have even dreamed of until recently. And as by now I've come to expect, they do this by messing with the very fabric of reality itself and by completely contradicting my existing ideas about physics. Maybe our understanding of black holes has been fundamentally wrong. However, to understand how a black hole seems to break the usual rules on faster-than-light travel, and does it in a way we could potentially use without having to go inside a black hole's event horizon, and how it also creates nearly limitless energy, we need to look deeper into the features of black holes than we have so far. It's actually quite hard to say much about a black hole's features precisely because of the event horizon. We can't see what the inside of a black hole really looks like. In fact, there are only 3 characteristics we can definitively assign to black holes with any certainty. They have mass, they have charge, and they have angular momentum. You might be wondering how we know these properties of black holes, since no light can escape them to bring us information. The key to these 3 characteristics is that they all represent aspects of the black hole that can be detected and measured outside the black hole's event horizon. Charge, for instance, works around a black hole just like it does around any other charged object. That is, if a black hole is charged, it will pull in objects with an opposite charge and push away objects with the same charge. Think of it as a giant magnet pushing and pulling on the universe around it. Scientists can watch objects as they approach a black hole, and by seeing how quickly certain objects with a known charge accelerate toward it, they can figure out the black hole's own charge. Interacting with this is mass. The mass of a black hole can also be detected outside the event horizon. In fact, it's the main creator of the event horizon to begin with. This is because mass creates gravity, and it does so in a linear way, following principles similar to Gauss's law in electromagnetism. So it's also possible to calculate an object's mass by watching how far away other objects are before they start to accelerate toward it, and how fast they accelerate, though you have to, of course, factor in charge at the same time to avoid getting wrong results. Finally, there's angular momentum, or spin. It's possible to detect the spin of a large, massive object, and we'll get into the how in a moment. For now, let's just accept it as a fact and acknowledge that black holes are indeed extremely high-mass objects. Black holes come in various sizes. The smallest known, called micro-black holes, have a mass similar to our moon, or 7.35 watts at 10 to 22 kilograms. They squeeze all this mass into a space just 2 millimeters across, which is truly incredible and gives you an idea of a black hole's amazing density, something thinner than a human hair containing the mass of the moon. And these are just the smallest ones. Stellar black holes have a mass equal to 10 times our Sun and a diameter of 60 kilometers. Intermediate black holes have the mass of 1,000 suns and pack all of that into a diameter of 2,000 kilometers, still much smaller than Earth. It's the largest black holes that really dwarf us, with masses from 100,000 to 10 billion times the mass of the Sun, and sizes from 0.01 to 400 astronomical units. An astronomical unit is the average distance from Earth to the Sun. Apart from these three features, in theory, there are no other differences between black holes. If you were to put two black holes in the same room and make sure they had the same mass, charge, and spin, it would be impossible to tell them apart. However, these three features are enough to create some amazing effects in the region of space outside a black hole. Traveling inside a black hole is, as far as we currently know, impossible. Space and time break down past the event horizon. However, we think we know a few things that must be inside one. Pulsating at the center of a black hole is thought to be the singularity. In reality, this is the black hole. When we talked about diameters earlier, that was just the diameter of the event horizon. Again, we're not sure what the black hole itself really looks like because light can never escape from it. In a space that is infinitely small, there's a point where all the mass of the black hole is crammed, making it infinitely dense. For the simplest models of black holes, the ones that don't spin, this is a single point. In a rotating black hole, this singularity is more like a small spinning ring. Otherwise, it would be hard to define spin for a point that has no volume. Our current understanding of physics gets extremely strange around such a black hole. If you follow ideal paths around this point, it becomes mathematically possible to do very strange things, like meeting your own past. This has troubling implications for causality and leads to time travel paradoxes like the grandfather paradox, which strongly suggests our current ideas about singularities are not quite right yet. Because the singularity is so infinitesimally small, we'll need a successful unification of quantum theory and general relativity theory to properly explain what happens inside a black hole, and we haven't achieved that yet. It may one day turn out that singularities don't exist at the centers of black holes at all, but this is as far as our knowledge currently goes. Whatever is inside a black hole, it provides the power for our hypothetical faster-than-light engine because, like most things in the universe, it spins. And indeed, it spins a lot. As we travel outward from the black hole's center, we cross the event horizon with surprisingly little drama. The event horizon itself can't be detected locally, although someone watching you from the outside would see you slow down to a complete stop as you cross it. From your own point of view, time might seem to be flowing normally, that is, until the universe outside the black hole lives out its entire existence in an instant. Because time outside the black hole is passing so quickly compared to your own experience. This is the very essence of relativity. In fact, the only sign you might have that you've crossed the event horizon at all is because of something that exists just outside it, the photon sphere. In a zone just outside the event horizon, there is a point in space where if a photon enters it at exactly the right angle, it will go into a perfect orbit around the black hole, much like the moon orbits the Earth. This infinitesimally thin zone is called the photon sphere, and given the countless photons that have passed by black holes over millions of years, it's likely full of them. It's quite possible you would be instantly vaporized as you pass through this point. However, it's just beyond here that we find the zone we're most interested in, the ergosphere. This is the area around a black hole where its spin is most easily detected, and this is because inside this zone, it's impossible to stand still. You see, mass affects space. We see this in the curving effect of gravity on the path of objects through that area of space. However, it might be more accurate to say that mass drags on the space around it as it moves, carrying a small piece of that space along with it. When an object as massive as a black hole spins, an effect called frame dragging happens. To put it simply, the fabric of reality around the black hole starts to spin in an inescapable whirlpool, much like a real one. Anything caught in the ergosphere is forced to spin around the black hole because the very frame of reference it's in is being pulled like a person moving because they are on a moving walkway. The more the massive object spins, the faster this happens, and in the ergosphere, this can happen at such a huge speed that by the time you reach the event horizon, space itself is moving faster than the speed of light. You would have to travel faster than light in the opposite direction just to stay relatively still from the point of view of an outside observer, which, of course, is impossible. But doesn't this break the laws of physics? Doesn't Einstein say that nothing can travel faster than the speed of light? The answer is yes, but black holes seem to have found an interesting loophole. You see, this rule only applies locally right where you are in your own frame of reference. Nothing can locally go faster than the speed of light. However, thanks to relativity, it's possible for frames of reference to move away from each other so fast that objects within them seem to be breaking this light barrier from your point of view. But if you were to move next to them and enter their frame of reference, they would appear to slow down and would once again follow the laws of physics. It's a very strange effect, but frame dragging is a proven phenomenon. It's by measuring frame dragging that scientists can figure out a black hole's spin. However, according to a physicist named Roger Penrose, there might even be a way to use this effect. If you were to launch a rocket into this part of the ergosphere, the rocket would speed up because it's caught in the whirlpool of reality. Once it had gained enough speed, it could then fire a propellant in a way that would shoot it out of the whirlpool, now moving at a much higher velocity. This method, called the Penrose process, could theoretically give you energy equal to about 20% of your rocket's mass. Now that might not sound like a lot, but remember that according to Einstein's E=mc2 equation, your 20% mass would produce energy equal to itself multiplied by 299,792,452. That is an astronomical amount of energy. So, to use this huge kinetic energy, all you would need to do is travel to the nearest black hole, which is about 3,000 light-years away from us, and enter its ergosphere with a rocket that can handle the intense gravitational forces there. Ideally, you would need to find one not surrounded by an accretion disk, as those reach temperatures of millions of degrees as they are thrown around at near-light speeds, melting from solids down to gas and plasma. But you get the idea. Easy. All right, maybe this is a bit impractical for us right now. However, the implications for faster-than-light travel that black holes show through frame dragging might just give us the key to one day truly breaking the light barrier, not by directly going faster than light ourselves, but by somehow making the frame of reference we are in travel at those accelerated speeds just as they do around a black hole. Of course, if this requires the energy of a black hole to do, we might be out of luck for now. But it gives an incredible glimpse into what is potentially possible, and scientists are already looking into the power of frame dragging for future space travel. But perhaps that's a topic for another video. In any case, this all just shows once again how our universe is indeed profoundly different from what we might have ever imagined. Here is another surprising fact about black holes that you might not have known. Falling into one is a lot harder than it seems. You might think it would be simple. After all, they are the ultimate cosmic vacuum cleaners, literally the biggest sources of gravity known. Shouldn't it be easier to fall into them than into any other object in the universe? You might have thought so, but paradoxically, your intuition is wrong. These galactic giants are one of the most difficult places in the universe to actually get into, so much so that during his lifetime, Einstein thought you couldn't get into them at all. And not only that, but black holes might even shoot matter away from them at speeds close to the speed of light. Shouldn't these objects be incredibly easy to enter, like a slide that gets steeper the further you go? You would expect to speed up more and more the closer you get to the black hole's center. However, while this is partly true, it is also partly false. You do accelerate so much that your speed will start to approach the speed of light. Nevertheless, in almost all cases, you will not find yourself getting closer to the very center of the black hole. And this isn't about some strange quirk of time or relativity, but something that would be observable from whatever frame of reference you're watching from. Confused? Don't worry. Let me explain using the real-world example of something called an accretion disk. At their core, black holes are remarkably simple. According to something called the no-hair theorem, black holes are said to be almost completely free of unique features, much like a head with, well, nothing on it. The characteristics of a black hole are typically quite plain. They have charge, mass, and spin, and that's about it. As such, accretion disks are not a required part of black holes. They can exist just fine without them, sitting dark and unseen in space. However, when matter, like an unlucky star, gets too close to a black hole's gravity, it can be torn apart by the immense forces and pulled toward the black hole's center. Strangely, this matter doesn't just fall straight into the black hole's event horizon. Instead, the matter usually forms a kind of flat ring that orbits around the black hole outside the event horizon. While it all eventually goes in, this process can take a very long time. Some accretion disks need 100 to 1,000 million years to be completely swallowed. So, what's going on here? Why doesn't the matter just go into the black hole? The answer is in a surprising principle of physics called the conservation of momentum, first described by mathematician John Wallis in 1670 and later supported by his contemporary Isaac Newton about a decade later. The idea is this: if you have a group of objects, their total motion, their momentum, must always stay the same. If one particle with momentum hits a stationary particle and both then bounce off each other, the total amount of motion for the two particles combined must be equal to the starting amount of momentum of the first particle alone. No momentum can be lost. If you have a rocket on a launch pad with zero momentum, it can only create momentum for itself by pushing propellant out in the opposite direction. Once you add up the amount of momentum given to the air by the downward moving propellant and the amount of momentum given to the rocket by its upward movement, then the upward momentum and the downward momentum are equal, resulting in the same net zero momentum you started with. This idea might seem to go against our everyday experience. After all, we humans often stop and start walking around without seeming to follow this law. However, if you look at all the particles involved, this law is always followed. You would have a hard time moving anywhere without a surface to push against. The momentum given to the floor must equal the amount of momentum given to you, but in the opposite direction. You just don't notice it because the floor is so much more massive than you that the amount of momentum you give it doesn't cause it to move in any noticeable way. But what does this have to do with falling into a black hole? Well, consider this next example, this time about angular momentum. Imagine a ballerina with their arms stretched out, spinning on one point. The particles in their hands have momentum. They are moving a certain distance in a certain amount of time. However, when they pull their arms close to their body, what happens? They suddenly start spinning much faster. This is a classic example of momentum trying to be conserved. You see, the momentum in the hands is still trying to travel at the same speed it was before. But because it's now closer to the body, it's traveling a much smaller distance, but doing so at the same speed. In effect, it has a much shorter distance to travel to complete one spin, and as a result, it completes that spin much faster. This makes the ballerina spin faster when they tuck their arms in and slower when they stretch them out. Now, imagine this on a cosmic scale. In most cases, matter doesn't fall in a perfectly straight line toward a black hole. Almost always, it will miss it slightly and will start spiraling in toward its center as it's caught by the black hole's gravity. It now has angular momentum. As it gets closer to the black hole's center, it starts speeding up, moving at the same speed but in smaller and smaller orbits, gaining more and more angular spin the further down the gravitational well it falls, just like the ballerina. If you want to move a little further in, you have to spin a little faster. But unlike the ballerina, this matter has to deal with the speed of light. Nothing in the universe can travel faster than the speed of light. This is a fundamental law discovered by Einstein. So, what happens to our spinning matter as it falls further and further into the black hole? Because of the huge forces and curvature involved, it eventually reaches a point where it can't speed up anymore. It has hit a roadblock, and because it can't spin faster, it can't fall further into the black hole. This has several major effects. To start with, as you can imagine, this creates enormous friction. All this matter spinning at such incredible speeds around the edge of the event horizon starts colliding with itself, and when these collisions happen at near-light speeds, things get incredibly hot. Matter in a black hole's accretion disk can reach temperatures up to 10 million Kelvin. This is hot enough to melt anything down to a hot plasma. These constant collisions smash the atoms involved, causing them to release more and more of this energy, like squeezing a lemon. This process reduces their mass. Between 10% and 40% of an atom's mass is turned into energy this way, which then radiates out across the universe. For comparison, nuclear fusion, the process happening in the sun, turns only about 0.7% of mass into energy. Let that sink in for a moment. Think about how bright the sun is at 0.7% conversion. How bright can a black hole's accretion disk get? The brightest such disks are known as quasars, and they can be so luminous that they outshine the total brightness of every star in the Milky Way combined by 1,000 times. The good news is that, in addition, some of that momentum starts to be shed with the escaping energy. More momentum is shed by passing it to matter further out from the accretion disk as fast-moving particles collide with slower particles orbiting just above them, giving them an extra push and at the same time slowing down the lower particles. In this way, matter starts to lose its angular momentum and eventually begins its final plunge into the black hole itself. More momentum can be shed through one of the most striking features of quasars and black holes, their jets. We don't fully understand everything about these jets, how they form and what they're made of, and only a small fraction of black holes with accretion disks have them. However, current theories suggest they are caused by powerful magnetic forces created by the spinning accretion disk, or even by the rotational energy of the black hole itself, which pulls material from the accretion disks and shoots it into space. It's likely that as the accretion disk spins, magnetic fields form according to Ampere's law because of all those moving electrically charged particles. The power and shape of these fields are such that there is only a narrow channel at the black hole's north and south poles for particles to escape. These magnetic fields may work in a similar way to the rifling on a gun, channeling particles down a narrow barrel. Particles moving at near relativistic speeds have only one direction they can go, even though we don't yet fully understand why they go. Perhaps they are like the steam from a kettle, forced out through the only available opening in the face of incredible gravitational and thermal pressure. And when they go at tremendous speeds. Relativistic jets stretch further than the galaxies they come from, often spanning millions, if not billions, of light years. One such jet, with a rather forgettable name, emits X-rays that reach Earth from 7 billion light years away, though faintly. This is because the radiation from such jets is highly focused in one direction, an effect known as relativistic beaming, or the lighthouse effect. When the beam is pointed away from us, it's much harder to detect. Take, for example, the now famous M87 galaxy. Here, a relativistic jet is clearly seen by the Hubble Space Telescope. This is the jet pointed toward us. There is very likely another jet, but we can't see it because it's traveling in the opposite direction. It's important to note that this energy doesn't come directly from the black hole itself. Remember, nothing can escape from a black hole. Instead, the matter and radiation come from the accretion disk around the black hole. And again, much about these jets is still theoretical. We can see them and even watch their movement over time, but our understanding of how they form and what causes them is incomplete. Our current understanding of accretion disks doesn't even fully explain how the conservation of momentum is maintained. There's still some mystery about where all the momentum goes, but the sheer power involved is undeniable. Einstein may have been wrong. It is clearly possible to fall into a black hole. However, when some black holes are throwing material away from them at near relativistic speeds for distances spanning galaxies, it is clearly also possible not to fall into them. And once you factor in the force of matter, millions of degrees hot, pushing outward as it tries to shed its own momentum, perhaps you wouldn't want to get too close to one anyway. So, we have witnessed how the incredible effects of a black hole can reach across entire galaxies, but this raises the question, just how big can a black hole actually get? Finding the largest black holes isn't hard. You just need to look at the centers of large galaxies. These supermassive black holes have been growing continuously since they formed billions of years ago. with more and more matter falling into them, constantly adding to their mass. The very largest of these supermassive black holes can have masses billions of times that of our Sun. However, it might be surprising to learn that some of the most massive black holes we know of are actually among the youngest. You see, when we look at distant galaxies, we are also looking back in time, and the galaxies that are billions of light years away often have the largest black holes. If the universe is only 13.8 billion years old, and light takes billions of years to reach us, that means the galaxy we are looking at can be, at most, only a few billion years old from our point of view, quite young for a galaxy. Surely, though, it should be the case that closer, and therefore older, supermassive black holes are more massive, since they have had so much more time to eat in falling matter. So, what is going on here? The largest known supermassive black hole is called TON 618, with an incredible mass of 66 billion solar masses. By itself, its mass is comparable to that of the entire Milky Way galaxy. However, TON 618 is extremely far away, and light from it has taken 10.8 billion years to reach us, which means we are seeing it as it was 10.8 billion years ago. This means it can be at most about 2.8 billion years old. In comparison, our own Milky Way galaxy is about 13.6 billion years old, yet the supermassive black hole at its center, Sagittarius A, is only 4 million solar masses. The Andromeda galaxy's supermassive black hole, while bigger, is still only 200 million solar masses. One major factor to consider here is how hard it is to detect and measure black holes. This is still a relatively new field of research, as technology has only recently allowed us to start observing black holes in the last few decades. Even then, we can often only see the areas around black holes, that is, before the creation of the Event Horizon Telescope. But even that telescope takes a lot of time to image just one black hole, so our general understanding is still quite limited. In fact, most of the distant black holes we know about can only be seen because they are quasars. TON 618 is a quasar. Matter is pouring into its accretion disk at an amazing rate, and because of this it has lit up into a quasar. Quasars can only stay lit as long as matter is actively falling into them. Otherwise, they go back to being dark black holes. It's hard to fully grasp the physics of the accretion disk, but it's believed that the friction inside it is so immense that the accretion disk of a quasar by itself can produce thousands of times more light than entire galaxies combined. TON 618 shines as brightly as 140 trillion suns, completely outshining the galaxy it's in, to the point that we can't even see the galaxy itself from where we are. However, because quasars are the most luminous objects in the universe, they can be seen from very great distances. So, one reason for the large number of big black holes at great distances is due to something called Malmquist bias. This phenomenon means that brighter objects that are further away seem more numerous, when in reality, we just can't see the dimmer objects at that distance, which suggests that there might be an argument that the largest supermassive black holes are actually spread out fairly evenly throughout the universe. If a galaxy has a very large black hole, but it isn't a quasar, it means we won't see it beyond a certain distance, because a galaxy is much dimmer than a quasar. Another reason why we don't see the largest black holes in our immediate cosmic neighborhood is due to the nature of the universe itself. Shortly after the Big Bang, as you may know, the universe has been constantly expanding, and during the early universe, matter was much more densely packed. Quasars were more common then because they need huge amounts of matter flowing into them to shine, and there was much more gas available during the early stages of the universe. Not only has the universe expanded, but over time, gas is turned into stars. Some of the largest types of stars eventually become neutron stars and black holes themselves, which means they never get recycled back into gas. Less available gas means less gas will fall into a supermassive black hole. One of the main theories for the universe's ultimate fate is actually based on this idea called the Big Freeze, where after several trillions of years, all the gas in the universe is eventually turned into black holes. Even now we see some galaxies where their gas has been completely used up, which means no new stars can form. These are called elliptical galaxies. Spiral galaxies still have gas and dust structures, and so can keep making new stars. It's interesting to note that most of the largest supermassive black holes seem to be in elliptical galaxies, where there is no gas left. Gas needs to lose momentum to fall into a galaxy's central supermassive black hole, and if that has happened, then the supermassive black hole is likely to be much bigger because of all the infalling matter. In elliptical galaxies, this process has already mostly happened, whereas in spiral galaxies it hasn't happened as much. One such trigger for gas losing angular momentum could be the gravitational pull of nearby galaxies or even collisions with other galaxies. Additionally, there is less gas available in the universe now than there was during the early universe, so black hole growth probably happened quickly then, but has slowed down in the present era. This might explain why there is no quasar within 500 million light-years of us. As the universe gets older and cosmic structures become less chaotic and more spread out, the number of active quasars has consequently gone down, which means that the only quasars we see, some of which are the largest black holes we know of, are those that existed a long time ago. So, why are the largest supermassive black holes often seen as the youngest? While it may look that way, it might not actually be the case at all. We can measure distant bright quasars simply because we can see them. Older and closer black holes may also be massive, but because of Malmquist bias, we haven't found them yet. As studies continue and technology gets better, we will slowly get a more complete picture of the universe around us. We have talked a lot about black holes as they are fascinating areas of space-time where curvature is pushed to the limit. They show features and phenomena that go far beyond any intuition we could get from classical physics on Earth. Yet, despite all the attention they've received, black holes are not the only way space-time can show its beautiful curves. In theory, there can be equally curved regions of space-time called white holes, which get their name because they are in many ways the exact opposite of black holes. And in some cases, a black hole and a white hole can be connected by a completely different type of space-time called a wormhole, which acts as a kind of limbo zone between parallel universes. If you have heard of space travel through wormholes and thought it was nothing more than a fanciful science fiction idea, I don't blame you. After all, even though these regions are theoretically possible, there is currently no experimental evidence that white holes or wormholes actually exist in our universe. But a century ago, black holes were purely theoretical, and now we believe there are literally billions of them out there for our telescopes to see. So in this discussion, we will try to answer three basic questions. What exactly are these other holes that can exist in space-time? Should we hope that they might be more than just science fiction? And what would they look like if they are indeed real? Join me today as we explore the different types of space-time that can result from extreme curvature. I believe the possibilities will bend your mind as much as they warp the fabric of the universe around them. Before we get into the complex physics of space-time, as described by Einstein's theory of general relativity, I want to start with a simple analogy. If I ask you to picture a cone, you will probably imagine either something that points upward, like a traffic cone, or something that points downward, like an ice cream cone. These are what we usually think of as cones in the real world. However, if you write down the most general mathematical equation for a cone and try to graph it, you will get something that looks like two cones glued together. You see, a mathematical cone has two halves, one that points upward and one that points downward, connected at their tips. And what we think of as cones in the real world are, in fact, just shortened parts of the complete mathematical cone. Black holes work in exactly the same way. Let me explain. Many of the black holes we see in the universe are the leftovers of massive stars whose extreme gravity caused them to collapse in on themselves. Once a black hole is formed, it becomes permanently cut off from the rest of the world by a spherical boundary called the event horizon. Anything can fall into the black hole, but nothing, not even light, can get out. This space-time structure can be elegantly shown in what physicists call a Penrose diagram, which is a way of representing an infinite space-time in a finite drawing. The key feature of a Penrose diagram is that light travels upward at 45-degree angles, making it easy to see which regions light can or cannot enter. In this diagram, Region 1 represents the regular universe, containing the original star before it turned into a black hole, and everything outside it, from the infinite past to the infinite future. Region 2 is the black hole, and is separated from the rest of the universe by its event horizon. You can see how easily light can enter the black hole region, Region 2, but it is impossible for light to get out. It will always hit the singularity instead. The same is true for ordinary matter, which moves slower than light, and so, in this diagram, can only travel upward at angles steeper than 45 degrees. So, what is so special about this Penrose diagram? It accounts for the black hole's formation at a specific point in time when the star collapsed. In the distant past, there was no event horizon or black hole to speak of, and light could travel freely across all of space. But while this diagram represents the kind of black hole we are used to seeing in the real world, it is only one part of the complete mathematical description of black holes in general relativity. In other words, it is the single ice cream cone of black hole diagrams. So what happens if we ignore the real world and imagine an ideal black hole with an infinite past, getting rid of the baggage of collapsing stars and everything else in the physical universe? What is the black hole equivalent of the full mathematical cone? It might look like a simple extension of our original Penrose diagram, but this diagram introduces a somewhat inverted physics. Region 1 is still our regular universe, and Region 2 is still a black hole with an unavoidable singularity in its future. However, the mathematics also describes something that looks like the inverse of a black hole in Region 3. Instead of a singularity in its future, Region 3 has a singularity in its past. And if you plot the movement of light rays at 45-degree angles, you will see that it is easy for light to leave Region 3, but it can never enter it. This type of region is exactly what we would call a white hole. It is the space-time equivalent of a traffic cone. But that's not all. If you look beyond the white hole, you will see a patch of space-time labeled Region 4, with the same connections to the black and white holes in the middle of the regular universe. This patch is a parallel universe, and it is completely disconnected from the universe in Region 1, since it is impossible for even light to travel from one region to the other. The upshot of all this is that the same mathematical equation that describes the regular universe and the black hole also describes the parallel universe and the white hole. This doesn't mean that every black hole comes with a white hole. Just like with cones, the real universe can have shortened pieces of the full mathematical solution. But it does mean that even if white holes are less common than their black hole counterparts, or even if there are no white holes connected to our universe at all, it doesn't make them any less scientific in the sense that they are equally consistent with the laws of physics. In our analogy, if you imagine that ice cream cones stay extremely popular while traffic cones become hard to make and are phased out of existence, that doesn't make the concept of a traffic cone any less real. This is more or less the current status of white holes. The idea of a white hole makes perfect sense, but it's possible that any white holes that existed in the past were unstable and were similarly phased out of existence. If you are wondering whether there could be more stable white holes that have just escaped our detection, you are not alone, and you should keep reading for when we discuss the tiniest possible white holes in just a few moments. But first, I want to make sure we are not leaving anyone in suspense. I promised you wormholes. I promised you parallel universes that are actually connected to each other. So brace yourselves, because we are about to go to a whole new level of warped space-time. The no-hair theorem says that a black hole can have up to 3 basic properties: mass, charge, and spin. However, the Penrose diagram I showed you before only described the simplest kind of black hole, one that was electrically neutral and completely still. The diagrams for charged or spinning black holes are much more complex, but they are also much more exciting precisely because they fundamentally change our understanding of singularities and give rise to new and fascinating regions of space-time. Let's look at the Penrose diagram for a spinning black hole as an example. Instead of 4 different regions of space-time, there are now 8 types of regions that repeat themselves in an infinite pattern of universes. Regions 1 through 4 are the same ones we saw before: the regular universe, the black hole, the white hole, and the parallel universe. But now that the black hole is spinning, its geometry no longer has an unavoidable singularity in its future, and the white hole similarly loses the singularity that existed in its past. So, what actually happens after you cross the event horizon of a spinning black hole? At first, you would be pulled toward the black hole's center, just as you would expect. But eventually, you would cross a boundary called the inner horizon, beyond which the geometry of space-time unwraps, allowing you to stop yourself from falling even deeper. In these innermost regions, marked 5 and 7, you could theoretically float freely toward or away from the black hole's center. You could even touch the singularity if you wanted, though I wouldn't recommend it. Here, in these innermost regions of a curved, rotating space-time, you are officially in a wormhole, and if it weren't for the fact that you are permanently separated from everyone who stayed in Region 1, this would have been the perfect moment for you to brag about your amazing space adventures. At this point, you are also faced with a sort of fork in the road. One option is to keep moving inward and go around the singularity, which takes the form of a ring rather than a point for spinning the black holes. This path would lead you to Region 6 or 8 in the diagram, but it's quite possible that the existence of this path is actually a flaw in the predictions of general relativity rather than a true description of reality, because even a single loop around the singularity can lead to causal paradoxes, where you visit your own past. A safer bet would be to turn around and move outward, recrossing the inner horizon from which you just came. This would take you into Region 3, a white hole, which would then carry you all the way out to a brand new universe, similar in structure to the one you originally left, but sadly, without your friends or family waiting for you. In fact, by the time you arrived here, your old universe would have already gone through an infinite amount of time. You would be living in a completely new definition of the future. Okay, let's get back to reality. As fun as that journey through the wormhole was in theory, you probably couldn't survive it in practice. And honestly, there's a good chance that the wormhole itself would collapse once you disturbed its space-time. So, how much of this mathematical structure can we realistically expect to see in the real world? Spinning black holes with event horizons seem to be everywhere in the universe, but what happens inside them is still largely unknown. There are two main reasons why the physics inside real black holes might be different from what the Penrose diagram would lead you to believe. First, when black holes form from the turbulent collapse of massive stars, some assumptions that were used to create the Penrose diagram are broken, such as the idea that the black hole existed forever, or that the surrounding universe is perfectly symmetric and doesn't contain randomly falling humans. Second, the theory of general relativity used to make the Penrose diagram might itself only be approximately correct, possibly breaking down near the singularity where the curvature is most extreme. So there is a good chance that some predictions of the diagram, especially the most problematic ones involving singularities and time travel paradoxes, are not actual features of a highly curved space-time. However, the existence of white holes presents a more open possibility, leaving plenty of room for speculation about how they might be created and whether they might leave any observational signs for us to find. One hypothesis that has recently gotten some attention is that a white hole is born whenever a black hole dies. And no, this is not some magical story of reincarnation or voodoo. It is a real attempt to understand the full life cycle of black holes with at least some mathematical support. You see, even an isolated black hole in an otherwise empty space will constantly emit particles known as Hawking radiation, causing it to slowly shrink and lose mass over time. But once the black hole reaches the incredibly tiny Planck mass, just about 20 micrograms, we have no way of predicting its future, at least not without a complete theory of quantum gravity. This is where loop quantum gravity comes in, a proposed link between gravity and quantum mechanics in which space itself is made of discrete loops. In essence, the equations of loop quantum gravity predict that instead of continuing to shrink even smaller than the Planck mass, such a tiny black hole is instead more likely to quantum tunnel into a white hole, throwing its contents back into the universe over a long period. Incredibly, even though this white hole would be similarly small and light, it could contain a huge amount of entropy because its interior geometry would have been stretched into a thin tube with an extremely large volume. This stored entropy could potentially open a path for any information that falls into a black hole to be recovered in the distant future, thereby solving a decades-long problem in theoretical physics known as the information paradox. As the white hole releases this information, it begins to slowly fade out of existence. The space-time around it loses its curvature, and its life cycle comes to an end. But before this video ends, let me leave you with one final thought. In general relativity, our entire universe is predicted to have had a singularity in its past, specifically 14 billion years ago at the moment of the Big Bang. In this way, the universe is like an uncharged, stationary white hole. But if loop quantum gravity suggests that white holes can be born when black holes collapse, could the same be true about the creation of our universe? Could it be that our expanding universe was born from the ashes of an older, contracting space-time? As bizarre as this seems, loop quantum gravity suggests that this may indeed be the case. However, there are so many different ideas for how this transition could have happened that we would need a whole new video just to scratch the surface.